So thank you, Wolfgang, for the kind introduction, and thanks also for the invitation. It's really a pleasure to be back in PTB, both to see people and interact in person and to see some people I know and to talk about things I was doing in the last years and would like to do in the next years. So I will tell you sort of two stories, one about neutrons and one about atoms. I think there's some contact to both neutrons and to atoms here at PTB. And so I'll try to emphasize some of the things which are maybe less in the direct PTB focus and draw the connections to things that may be more familiar. So let's start with a very high level summary of why this is an interesting thing to talk about. So this is my cartoon slide to illustrate for complete non-specialists what I am trying to do. You've seen maybe pie charts for dark matter and dark energy to say that we don't understand some 95% of the universe. Well, I'm here to tell you that the remaining 5% we don't really understand either, because in the end, all of this matter from which we get solar systems that have things like apples and neutrons inside of them, this needed to be produced in a way that there would be an equal quantity of antimatter. And the antimatter we don't see when we look out at the universe. So all of this matter had to get there somehow. And this actually has an impact on the smallest structures here. So the scales are not chosen randomly. If you take a solar system and you shrink it down to the size of an apple, this is some 13 orders of magnitude. If you look inside the apple at 13 orders of magnitude magnification, you see a neutron. And then to look for the signatures of this physics, we go then another 13 orders of magnitude inside the neutron to try to see if it has internal structure that may be a sign of the physics for explaining how we got back all of this matter at the largest scales. And then the technical summary I won't do in much detail, but I'm happy to answer questions about it. Essentially, we look out at the number of photons in the universe. This is the cosmic microwave background. And there have to be some photons from every time a baryon and an antibaryon annihilated. We can do the counting because we know about how much matter we see when we look out at the universe. And it's a very, very small asymmetry. So we have one extra baryon for every billion baryons that there were compared to antibaryons in the beginning of the universe. But this is, again, 10 orders of magnitude too much. And we need some ingredients that the standard model does not give us to explain this, in particular, violation of the discrete symmetries C and P. So the fact that we see none of this antimatter in the universe and that the standard model cannot break these symmetries by itself without new physics tells us, with no ambiguity at all, there has to be new physics or we wouldn't exist. So there's a discovery waiting somehow to happen, and the question is, what are the best tools to make it? And that's what I will try to answer. So here, the experimentalist picture of everything that we can look at to find the new physics is something like this. At a very high energy theory, sorry, go back now, we have all possible ways that these symmetries can be violated in some extension of the standard model, let it be supersymmetry, multi-Higgs, anything. And then these will have some impact at a lower energy scale on theory parameters, which we can write down or talk to theorists about. And then these theory parameters propagate down in energy scales into nucleons like the neutron and proton. The neutrons and protons are bound into nuclei, and now we talk about different states and matrix elements. But the ultimate effect is that the high energy CP violating physics is making some polarization moment in a low energy bound state. And by a low energy bound state, I mean a neutron or an atom or a molecule, something with a well-defined quantum mechanical ground state. And then each of these parameters is mattering differently for each thing that you could look at. So if I look at a neutron or a xenon atom, I will see a different combination ultimately of these parameters and a different combination, therefore, of the fundamental physics. And so what we should do is measure in many systems in order to see complementarily how the combinations evolve and from the low energy measurements, what might be existing at high energy. And basically, this is fully complementary to direct searches at colliders, but it has the advantage that if you want to go and try and excite new degrees of freedom, you have to use a high invariant mass and you have to collide particles at very high energies. So to win a factor of 2 or 5 or so is very hard at a collider. To build the LHC now bigger with better superconducting magnets and so forth And it's a linear improvement, but it's not an easy one because the technology is not a linear challenge. If we go instead in the direction of seeing more and more sensitive couplings, so we have more intense sources or more precise measurements, then we assume rather that the virtual corrections due to new physics are the sort of fixed size, and that we can see them by a suitably high resolution measurement in a system where we have many, many particles available already. And so our problem is not to make the high energies, but to make the precise measurement. And then you can think of this as complementary to looking back in the age of the universe to the highest possible energy scale at the earliest possible time. We simply take what we have now and we look at it as carefully as we can. So the electric dipole moment, the permanent electric dipole moment, is the example which is relevant in this context. It's a simple thing to imagine, essentially just a separation of charge along the total angular momentum of this quantum system that we choose. And this means, in addition to the magnetic energy shift, which you know and love, everyone here in Department 8 at PTB, I guess, we have an electric contribution with the same form. And this D would violate parity and time reversal symmetry. So people normally learn in their first quantum mechanics class that it's 0. But it can't be exactly 0, or we wouldn't be here. And so we have to find it, however small it is. And we do this by putting an electric field and a magnetic field together. And in one case, then, these two contributions are subtracting. In the other case, they're adding. And now by combining these two measurements, we isolate either the magnetic part, which controls the systematic effects, or the electric part, which controls what we want to know. And Ramsey, in the 1950s, gave us the technique to do this by interferometry of polarized nuclear moments. And so this is essentially a time domain interferometer between a particle and its own ground state. And so if you do exactly the measurement that Ramsey had with a magnetic moment, and you assume that there is an electric contribution at the same time, then the phase of the electric contribution adds, and after the second pulse, the spin projection onto the quantization axis will include a contribution from the electric dipole moment. Because it's an interferometric measurement, you measure a frequency, and this is basically the best that you can do in precision physics. So because this is the unifying theme underneath all of the noble gases, the neutron, the comagnetometry, I take a moment just to review what I think you all know already. This is spin precession of magnetic moments. You have a splitting of the state, and essentially the magnetic field is measured when you know the proportionality constant between the precession rate that you actually see in your experiment and the magnetic field, which is driving it. These equations of motion, of course, are classical, but you get the same ones if you solve the real quantum mechanical problem up to relaxation effects. And then the point which is interesting from the point of view of precision is that you have a time energy uncertainty between the energy resolution that you can reach and the time that you can measure for. And so if we think of it in terms of a frequency measurement, then the frequency resolution you get for looking at this phase shift that would arise from an electric dipole moment is simply proportional to the product of the dipole moment and the electric field you can put on, but this energy resolution is then inversely proportional to the measurement time. And the smaller the energy resolution you want, the longer you want to measure for. And then all you have to do is find the best way to look at this in terms of a spin precessing in a magnetic field. And then something which comes up as a conceptual challenge when people see that molecular dipole moments are written as a common thing in the literature and the water molecule has a dipole moment and so forth. Well, it's not the same thing because really the water molecule or the ammonia molecule here, where all of the electrons from the hydrogen atom are kind of grabbed around the nitrogen, this is an induced dipole moment. The molecule has a very large polarizability and therefore very soon at a very low electric field strength here below 1 or so, you actually have a quadratic scaling. When the molecule is fully polarized, it looks like a linear energy shift, but it's really because the molecule is already saturated. And if you go to 0, this parity violating, time reversal violating effect is not really there. So that's a subtlety which is worth appreciating when we often talk in quantum mechanics about similar systems, but it means something different. And then I think most people in the audience are familiar with what is here on the left. This is the xenon-helium comagnetometry experiment that Wolfgang and Jens and I and Allard and others have all worked on together from 2014 to 2019 or so. So this is a case where we have a continuously precessing nuclear spin. We measure it with squids. You all know this very well. With neutrons, it's a bit different, and the sensitivity equation is often written in a different way because we don't measure continuously, we count particles at the end of a precession cycle, but the scaling is similar. We have a measurement time in the denominator, we have some source, we have some precession cells, but we count particles, we don't see a continuous signal. In the end, the physics is similar, and it will be the same when I come back to polarized noble gases in the end and talk about a different way to do a continuous measurement with lasers rather than squids. Coming to the neutrons now, we talk about ultra-cold neutrons. Ultra-cold is another word which is often used in different ways by different communities. So for ultra-cold atoms, which are maybe more common, it's actually 5 orders of magnitude colder. Interestingly, the wavelengths are not so terribly far apart, and the counting statistics can be rather similar, but the phase space density is interestingly 13 orders of magnitude different. And that means, well, you can have a quantum degenerate gas of, for example, cesium atoms and make a Bose-Einstein condensate. With neutrons, you would need 13 orders of magnitude denser source to get this. And no one today has the technology for that. So the neutrons are like an ideal gas which interacts with itself to an excellent approximation, not at all. The cross-section for a neutron interacting with a neutron is so small that no one was able to measure it yet. And then if you want to know what this means in terms of neutron temperature, because neutron physicists often talk in terms of moderation temperatures, there's a very easy rule of thumb. You simply take 10 meters per second and count by ones in the exponent. So ultra cold neutrons are from 1 to 10 meters per second. Very cold neutrons are from 10 to 100. Cold neutrons are up to 1,000 meters per second or so. Then it breaks down, but thermal neutrons, 2 kilometers per second is a 300 Kelvin moderator. So we have to go down by a few orders of magnitude in velocity, but remembering that energy goes as velocity squared. This is many orders of magnitude in energy to reach the ultra cold regime where neutrons can be not only guided, but trapped. And when they are trapped, then we have a long measurement time because unlike an experiment fed by a neutron guide where a 2 kilometer per second thermal neutron will go through in milliseconds if your apparatus is some meters in size, for ultra-cold neutrons, we put them in a fixed place and we look at them for many minutes. And so there are, again, many orders of magnitude gain in sensitivity, even though these statistics are so low for ultra-cold neutron sources. And then since I put quantum sensing in the title, I want to explain a little bit what I mean by this. A quantum sensor for me is something which relies on intrinsically quantum effects to make a precision measurement. And in the case of neutrons, this could be a state-selective neutron detection, maybe not just a helium-3 detector, but something which resolves the neutron spin and ideally uses quantum mechanics in order to do so. For optical magnetometry now, this is sort of an intrinsically quantum thing. Whether the squid measuring a precessing magnetic field is quantum could be arguable, the squid itself, of course, but the magnetic field is kind of a classical thing. When we excite directly the internal degrees of freedom of the atom, and we do that in an intrinsically quantum process, then I think we can legitimately talk about quantum sensing. But the unifying theme here is, again, the use of interferometry in order to obtain the highest possible precisions. And so coming to the neutrons again for a moment, how does this work? What might an experiment look like? We have essentially an interaction potential of the neutron with everything. And everything in these cases is usually dominated by the nuclei of whatever matter it touches, the gravitational field of Earth, and any magnetic field that you might put on. And interestingly, all of these come in at about the same orders of magnitude. So here, mu dot B, this is the same as in the Hamiltonian for a precessing spin. And then this first term is a way to parameterize the strong interaction because the wavelength of an ultra-cold neutron is so large, it's averaging over many nuclei, and it sees them as a homogeneous medium with an index of refraction. So we basically talk about optics. And then you can easily imagine that for a high enough energy barrier or a low enough energy neutron, you may get total internal reflection. This is another way to think of neutron storage. The only difference from classical optics here is that most materials typically have an index of refraction for neutrons, which is less than 1. That means if you have a concave lens, it focuses, the opposite of what you normally see for light optics. And then for loss rates, this works similarly for atoms and for neutrons. If you have some dissipation process, a line broadening mechanism, either for nuclear spins or for excited atomic energy levels, then what you measure in an experiment is the sum of all the partial decay widths. And when you lose neutrons, it's a similar process. You can lose neutrons to absorption, to upscattering, to beta decay. And if you want to know how long the neutrons will stay in your bottle, then you sum together all of these processes as inverse time constants. And what you measure is the total loss rate that comes out by doing that. And on the right here, you see experimental data for what may actually come in your detector. So starting at 0 seconds on the left, we have an ultra-cold neutron source being filled up, and the saturation buildup that you see starting at 100 seconds and going to 1,100 or so, this is the accumulation of neutrons until the loss rate is balanced by the production rate. Then you have a saturated density and you don't get more. This is like building up nuclear polarization in a cell. And then at 1,100 seconds, the source is opened and the neutrons go to the detector. So all of them go in a big peak. This is on a log scale. And then the source is emptied, and eventually all the neutrons found their way into the detector. The difference between the red and the blue curves is kind of a funny one, because at 500 seconds, the ILL reactor shut down. Normally, that means all the neutrons are gone for any other neutron experiment. But here, 10 minutes later or so, we could still count something. Less, obviously, because when the red curve starts going down, we have only the losses. The production rate is now 0. But this illustrates how we can still do something interesting at long time scales that are normally not available to neutron physics. And then if we think back historically just for a moment, I find it really amazing that Rutherford himself predicted both the existence of the neutron. This is in 1920, so I think, 12 years before the neutron was discovered by Chadwick. And he predicted that it would be very difficult to work with ultra-cold neutrons. It should be maybe impossible to contain it in a sealed vessel. And indeed, it's very hard. But I'm amazed that this was done. This was written in a lecture in 1920, and we only in 2018, we celebrated 50 years of ultra-cold neutrons. So prophetic, yeah? So how does it work? How can we make ultra-cold neutrons and then do something with them? I tell you about the one technique that I specialize in. There are others, but the main advantage here is that you get the highest possible densities. If you need a high rate, you may do something different, but for a storage experiment, you normally have a fixed volume, and to get the counting statistics in a fixed volume, it is the high density, which matters. And so superfluid helium is another amazing thing. And it has this famous dispersion relation where starting from 0 momentum and energy, it goes up linearly on a phonon branch, and then it has a maximum and a minimum. And the minimum is famous for this roton phenomena. But for neutrons, the funny thing is that when they are free, they have a parabola dispersion relation. This is just p squared over 2m, 1/2 mv squared. And it crosses in 2 places, the superfluid helium curve, at 0 and at about 1 millielectron volt. And since it crosses in 2 places, there's an amplitude for an interaction that makes a transition between these 2 points. And this transition is an inelastic scattering process where one cold neutron with a millielectron volt of energy gives all of its energy and momentum into the helium by creating a phonon. This phonon then propagates in the helium, and the neutron has stopped. And when the neutron has stopped, the energy is now below, for example, the energy barrier of the walls of the helium vessel, and the neutron can be trapped inside, so it becomes an ultra-cold neutron. And like that, we can stop the neutrons in helium and do experiments. The reason helium is good besides this is that it's the only nucleus on the chart of nuclides which has identically 0 neutron absorption. So in the loss rate equation, the absorption of the converting medium does not appear. This is unlike solid deuterium or oxygen or whatever else you might imagine. And it means that only with helium can you extend this saturation buildup curve that I showed you here into the longest possible times for the highest possible densities. Otherwise, because you don't change the size of the cross-section of the interaction, you have only to work with the neutron flux, and that means you need bigger and brighter facilities, which of course help, but we should also use the fundamental physics. And so then here, this is just on the right what I already described to you. And if we do it in practice, this is the layout of the ILL beamlines. So here in the center, we have the research reactor of the Institut Laurent-Langevin in Grenoble. It sends in all of the blue lines cold neutrons. And you see immediately another example of why this is not a crazy thing to use the helium, because it can sit far from the reactor fuel element itself in a low background environment. This is good both for practical reasons, for radiological issues, but also for the background environment of a precision measurement. And so here at the top, we have the beam position of supersun where the liquid helium vessel sits. And you see again this many order of magnitude difference. So in the pile of the ILO reactor, we have some 10 to the 15 neutrons per square centimeter in second. In the cold source deuterium at 22 Kelvin, it's a bit less. At the end of the guide, we lost 5 orders of magnitude. And the remaining 10 orders of magnitude we throw away very quickly, making ultra-cold neutrons. This is simply the size of the interaction cross-section with the helium and the size of the helium vessel. Because the mean free path is 17 meters, we don't build a 17-meter instrument. Okay, so how do we optimize the neutron delivery subject to these constraints? We have to design some very fancy neutron guides. And so it was about 3 months of continuous running simulations to choose the geometry. It turned out to be an octagon because the helium vessel is a circle. Neutron guides are normally rectangles, and an octagon makes the compromise best between a circle and a rectangle. And then on the lower right, you see the simulations on the right-hand side compared to the measurement on the left-hand side when the guide was finally installed. This is just to qualitatively illustrate that it more or less worked. Obviously, we took the highest usable neutron flux that was calculated by the simulations. And then the cryostats, the source vessel, looks something like this. So we have on top a large orange cryostat, which is a helium-3 refrigerator. So this brings some tens of milliwatts cooling power at half a Kelvin temperature. And that's a very unusual thing because normally people want high cooling power at a higher temperature or some very, very low temperature with a dilution cryostat that you don't get much cooling power at all. But here we have a large volume. We need about 13 liters of superfluid helium at 0.5 Kelvin. And the reason it needs to be 0.5 Kelvin is that the inverse process of making an ultra-cold neutron also happens. You can absorb a phonon by the neutron, and it will go up, and this is suppressed only by a Boltzmann factor. But there's a scaling of temperature to the 7th power. So T to the 7 makes a big difference between 1 Kelvin and 0.5 Kelvin. When you're at 0.5 Kelvin, the limiting loss rate is the neutron's beta decay lifetime of some 800 seconds. Then the phonons don't matter at all because there just aren't any in the helium. There are only the ones produced by scattering neutrons, and the cryostat takes these away. So this is how we do. And to give numbers for how the production rate comes out, we're simply filling up a phase space in 3 dimensions of momentum. And we make something like 5 to 10 ultra-cold neutrons per cubic centimeter per second, with the full beam of 10 to the 10 shining through the liquid helium. So this is why we have to wait some time in order to have the neutrons. But once we have them, we can then do something, and we want this we want this storage time obviously to be as long as possible again, so that we can build up more until we do the next cycle of the experiment. It's obviously not efficient to iterate like this. Once you have the source running, you rather just use it for science, and so we need at the same time some kind of a test facility in order to check when we have an idea for a new coding or a storage geometry that might be sensible to try. Is it really working or is it crazy? And this is what a master's student of mine has done in 2019. And this was followed up by a PhD student from Doug Beck, who was staying with us at the ILL for the last few years and just recently defended his PhD, Tom Neulinger. This is a cryostat which has no helium in it, but it goes down below 10 Kelvin, and we can put it on a prototype source and do fill and empty measurements where neutrons come from the source, go into the bottle. We hold them for a time, we empty them out, and we see how well this bottle works. And it's much easier to make a small bottle and do this kind of test measurement than to dismount the entire liquid helium structure of the source and build it back up and see if we get more neutrons or not. So this has been a real game changer in terms of efficiently finding the path forward while not blocking the science that can happen at the same time somewhere else. But there's a lot of other neutron physics that has to go on at the same time, because we care not only about the loss rates, but also about the energy height of the barrier that makes the storage bottle. And the energy height is essentially something that you can measure also with cold neutrons, where the statistics are much better. So this is a one-dimensional quantum mechanics problem now with barrier penetration or reflection. And here on the upper left of the plot, you see exactly this total reflection plateau. So this is a reflectivity of 1 when the momentum transfer of a cold neutron is very small. When you exceed the critical angle, now some of the neutrons penetrate, they're no longer reflected, and this shows up as a loss in the detector, which looks for the reflected beam, and then going farther to the right, you see the interference fringes, because of course, there is some residual probability to be reflected, and this interferes when the substrate is reflecting and the surface of the film is reflecting. And so we can measure both the film thickness and the momentum transfer for total reflection, which tells us the energy height of the barrier. This is half the story, and the other half, of course, is the loss parameters. And so on the left side now, we have plots showing the ultracold neutron energy on the horizontal and the loss probability per wall interaction on the vertical. And you see this is a strongly nonlinear function. So you want a high energy barrier and a very low energy neutron so that it can interact with the wall many times before it would be lost. Ideally, of course, you want a high energy barrier together with a low loss cross section, but nature is not that kind. Usually you get one or the other. And so how do you deal with this situation? It's actually conceptually simple. You start with something that has a high energy barrier, even if a high loss, and then you put a low energy barrier with a low loss on top so that the neutron can penetrate through the top layer without being lost. Then it has the chance to be reflected, and it interacts with the second layer at lower energy. So you're farther down in toward the low probability to be lost on these strongly nonlinear curves. And like this, we were able to reach the highest densities of 200 neutrons per cubic centimeter or so inside the liquid helium source. And when we measure for a particular material the storage time in the test bottle, we see a certain number of neutrons surviving after a certain holding time in the bottle. This makes a nice exponential curve. And you can see that at room temperature, in the red, the exponential decay constant is much faster than at cryogenic temperature in the blue. This is essentially because the scaling of loss processes depends on thermal excitations. And when you have a slow neutron interacting with phonons, not only in the helium, but in the wall, or a moving, vibrating atom can scatter up, these degrees of freedom become frozen out at low temperature. And so actually a cryogenic source is already a good thing in the first place, and we can reach some 500-second storage times at low temperature, 300 or 400 seconds at room temperature, which is a significant fraction of the 800-second beta decay lifetime in the first place. Sometimes it's not quite so straightforward, and you see this isn't a beautiful single exponential. What we have here is kind of phenomenologically modeled by a double exponential decay. And the reason that you might explain a double exponential without being extremely rigorous is if some neutrons get lucky early in the storage time, they hit with an angle that the interaction with the wall depends on a momentum less than the total momentum of the neutron. And so they can be reflected then, but if they're not reflected specularly, they come back the next time at a steeper angle and they go out. So they're quasi-trapped, one might say. They survive a certain length of time, and this is the fast decay constant that starts. And then you have the second population component where really the total energy of the neutron, if it hits the wall, normal incidence, it will really be reflected. Then these are contributing to the longer decay constant at longer holding times. That is all that's left over. And so you have to be a little bit careful analyzing the data, particularly when you compare different neutron sources that are based on different technologies, because the ratios of these populations may be different. And even if you build your experiment up or down half a meter, this shifts the energy by gravity. And so to give an idea of the scale, 200 nano EV, 250 right there in the middle of the left-hand plots, this is about the best material that we have to make a wall barrier. Going 1 meter in gravity is 100 nano EV. So 1 nano EV per centimeter. The experiments that use such things, of course, must also consider this. So in PANIDM, the experiment served by the supersun source, we have this double cell geometry that I showed just quickly before. It's 37 centimeters between the top cell and the bottom cell. And so therefore, the energy distribution in the two cells is completely different, and the switching of magnetic field and electric field orientations is important, not only to do the standard EDM sequence, but to make sure that there is no correlation of a systematic effect with the high energy on the bottom versus the low energy on the top. And then these are many components that we've just had to build and test. This is a standard slide that I just show for a moment. I'm happy to answer questions, but I won't go into details now. And the installation in the guide hall looks presently like this. So we have this source, this 7 on the left-hand CAD image is super sun. This provides the ultra cold neutrons, and everything that we have to work with is fitting inside about 100 square meters. So this is a clean room. For the laser system, the magnetic shield supplied by a Medco that I think you all know, and all of the pumps for the cryostats, the detectors, the polarizers, everything for the EDM experiment as well as the source is fitting in here. And of course, on the right-hand side is the cut view of the Medco shield, now shown with the vacuum chamber and the pan-EDM storage cells built inside. So it runs like this. But how can we do better? The problem with this configuration of SuperSun and pan-EDM is essentially that you may get 200, 300 neutrons per cubic centimeter in the source, but you don't do the experiment in the source. You do it in the pan-EDM cells, which are some meters away. And it's like a gas. If you have a balloon and you fill it into an evacuated bottle, the density equilibrates. And so you have a volume ratio and you have losses on the way. And what we hope we get at the beginning of a storage cycle in pan-EDM is about 3 UCNs per cubic centimeter. 2 orders of magnitude lost again. We already lost most of the orders of magnitude that we can afford to lose. So might it make more sense then to do the experiment where the density is already high? I think so. This is hard, of course, because now you couple the problems. The conceptual distinction of a source which sits here and an experiment which sits here that can commission and work a bit independently, this is nice. So now we have to think how to do it in a modular way if the experiment sits inside the source. And the way that I propose to do this is a project which I started just at the end of my time at the ILL, and I'm trying to gain some momentum for it now at Heidelberg. We call it EDM to the N. And the idea is to have N cells along a line. I mentioned quickly this 17-meter mean free path. So one of the problems with inefficient usage of the neutrons is that SuperSun is about 3 meters long. After 3 meters, 85% of the neutrons that were in the beam in the first place just hit the beam stop. So they don't get used at all. And if you would go 6, 9, 12 meters, there's not a full order of magnitude to be gained, but this is a field where we fight hard for factors of 2. So it's reasonable to consider, but you have to imagine now, let's start with 1 cell or 2 cells. Do it proper, find the right way to build the cells, and then when this is clear, the cryogenics is more or less scalable. This is nothing more ambitious than was done for SuperSun already, but you may have to repeat it several times to get the full statistics reached by combining these cells. You have the high density inside the cells, so this is a place where you can win 2 orders of magnitude or so. And inside the liquid helium, you have the possibility to put an electric field, which is about 3 times stronger. So all of these are parameters which matter a lot in the context of an EDM measurement. We still worry about the storage time, and we worry about systematic effects, and we worry about magnetic shielding. But since the field is completely limited by neutron statistics, this is the problem that we have to take first. And so imagine that we would build just a few cells. We have to get the high voltage in, and we have to now measure the neutrons as well. So for me, this is the real challenge, because if you let the neutrons out to a detector, then you suffer the same transport losses and everything that you have already in pan-EDM, and in almost every other EDM experiment using ultra-cold neutrons, which is currently planned. The problem then is to build a detector which sits inside the experiment. And this is maybe the only really new concept in this idea. Everything else is based on things which were either demonstrated or rather straightforward generalizations of what was already done. Here, you want something which can detect the neutrons inside the cell, but it should not poison the storage volume. It should not be detecting the neutrons before the experiment is over, otherwise this is a loss rate. And so how do you turn the detector on and off? Well, you may use a magnetic field. And the magnetic field, as you remember, the energy barrier is tuned up or down by mu dot B, depending on the spin state of the neutron. And so now this is your spin-dependent quantum sensor, which will see one spin state repelled out from the detector and the other one dragged in. So what we want, in fact, is a very, very small but very, very steep field gradient just at the surface of this coating. This can be built with a superconducting microstructure, and it can be measured with cold neutrons in the same way as the storage coatings themselves. You have to obviously take great care that by doing this, you don't make magnetic field gradients which are unacceptable in an EDM experiment. But the 2 points that I would draw your attention to for this are that one, the detector is not turning on until after the second Ramsey pulse. So the neutrons are all in their quantization axis at that point. And second, a coil which makes a strong magnetic field gradient and you can put a current through is also a degaussing coil. And so you can run a cycle where this cleans up after itself. And you start the next measurement cycle clean. The Ramsey pulses go, the neutrons are detected, and now maybe, yes, something is polarized, magnetized in the wall, but then you degauss and you start again fresh. This is a real challenge to do, but it's fortunately the kind of challenge where you can build a small sample of some centimeters squared and take it to the FRM2 or the ILL and iterate it like this, rather than building a 2 million euro instrument and iterating like that, which works not well, I can promise. So there is some hope to decouple these problems, and then the storage cells to be tested one at a time or so becomes also a scalable problem, and you can imagine a demonstration experiment using a cryostat on the user beamline that then proves the case that it may make sense with magnetic shields and so to continue going forward. So this is the concept I want to communicate for the path forward. I certainly can't promise 2 or 3 orders of magnitude in sensitivity based on what we know today because there are question marks left, but as of right now, this is the only path that I'm aware of that even goes in that direction. So this is some detail on the detector telling just what I did before, that you have an energy barrier here. The neutron is now being absorbed after this magnetic field shifts it up or down. So the straight line, the solid one, is one spin state. The dotted line is the other. And you'll notice that this is not all or nothing. You don't fully cancel the barrier of the storage potential, but this is where UCN are again your friends because they interact with the walls many times, and each one has many chances to go in the absorber. And in fact, what this determines is just how long you have to count for at the end of an experimental cycle. So the parameter space for it looks like this on the left, and an example of a test wafer would be something like this on the right, where you have a meander pattern of oppositely directed currents carrying underneath the absorber layer whatever you decide to put on from the outside. And we can discuss this if people are curious, but basically the green region is the range of energies which can be efficiently detected in such a system. The low edge is determined by the detector current. You turn it up, this makes a larger magnetic field, so the barrier splitting is large between the 2 spin states. This brings you down to a certain energy. And the high edge is determined by the thickness, because anyway, you have some evanescent penetration of the neutrons, which are partially reflected or well reflected into the absorber. And even when the magnetic field is off, they have some probability to be counted. This is really just to illustrate, though, that this is a problem relying on known physics, which we can calculate, we can simulate, and then test. And so in principle, nothing has to hide. We can actually just go and figure out if it works the way we think. The storage cells are a different problem because ultra-cold neutrons are notoriously hard to simulate and calculate for. There you don't have much option except to go and test something. And so this is what I've done at the ILL in October, just before the long shutdown that has now begun. This is a quartz cell, basically the kind of geometry that I showed in the cartoon slide. It's about 10 centimeters in diameter and 10 centimeters in height, which is extremely small for an ultra-cold neutron storage volume when you think that 1 neutron per cubic centimeter. This is a volume of about 3/4 of a liter, so there are not many neutrons in there. But there could be, if we had it in a liquid helium source, 100 times more. And this is then to see, can you build a cell like this? Can it store neutrons efficiently? Does it make sense to proceed in this way? And so, okay, the CAD image on the right shows how it's done. The neutrons can be filled from the top. You have a valve, which is basically pushing or pulling a disk, which opens or closes a hole. The same on the bottom, and the neutrons go out at the end of the storage cycle to a detector, which sits underneath the vacuum chamber. And this is another place where gravity actually is our friend now, because by falling 1 meter, the neutrons gain enough energy to cross the window at the entrance of the detector. And then they're absorbed on a helium atom, and we count a neutron of it. The data looks something like this, and I'm showing here just the longest lived storage component because we went to a flux source, which has quite some high energy distribution, but this is a time constant on the order of 250 seconds or so. What was noticed in the process of obtaining this was that if you fill the neutrons from the top, then you actually, of course, you can see it immediately, you get the high energy neutrons which got over the hill. So you better fill from the bottom, and now you have enough statistics to see this, but we're on the order of 250 seconds already in the small cells of this size. So I should say that the EDM cells for PAN-EDM or PSI or any other extraction-based neutron EDM experiment are typically about half a meter in diameter in order to get the number of neutrons large. But this also means the time between wall interactions can be large. Here, the neutrons are crossing the cell 5 times more often. They interact with the walls 5 times more often. You would expect a significant impact on the storage lifetime. But 250 seconds is actually not bad at all. That's about the target for present generation neutron EDM measurements, and this was the first data that was taken here. So we have some work to do, but the first signs are not so bad. Now, the second story. Noble gases are another way to look at EDMs. This provides access to a second set of parameters that would point in the direction of different new physics sources. And I'm going to focus on a new way to look at them. So the idea of two-photon excitation is not new. This was another example of something that was described quite early in the 20th century, predicted by Maria Goeppert-Mayer. And you can see here 2 photons being absorbed, relying on the presence of a third virtual level. This was in her PhD thesis. And the observation was finally done in cesium for the first time in a pure atomic system by Isaac Abela in 1962. Interestingly, Isaac Abela was the guy at the University of Chicago who first told me I should think about doing physics research. I didn't realize that this was his background until after he died in 2016. But what he had done was to use a ruby laser, because this is 2 years after the invention of the laser. There was no dye laser, there was no diode laser. You have to now tune by temperature. And so he cooled his ruby crystal to minus 160 degrees Celsius. And then he fiddled more with the frequency by changing the firing rate. And he wrote in what I think is a fantastic understatement that it was extremely difficult to adjust the wavelength to the cesium line. But he's done it. And what you see here on the left, these are reference lines. So wavelength increases toward the right. And when it's a bit farther to the right, this is off resonance. The upper plot, this is just the excitation. And now when it hits the resonance by being at the correct wavelength, this bottom line is the fluorescence from the cesium. So it's flat here. And then he had the signal from 2-photon absorption. So I think this is fantastic. But today, cesium is the easiest atom to do 2-photon absorption because you have diode lasers at convenient wavelengths, and alkalis are available in abundance. You can heat a cell and get fantastic vapor densities. We don't have any of the same problems that he had in the 1960s. What we do have are problems with noble gases. And noble gases, you can understand the problem most easily just from the equation, because for absorbing n photons, this is a nonlinear process. You have to have all of the photons in the same volume at the same time, so to speak. And now you have to go by the product of all the dipole matrix elements divided by all of the energy defects from the virtual states that provide the excitation pathway. And this is terribly inefficient for noble gases because the excitation energies are so high that we talk automatically about ultraviolet wavelengths. And ultraviolet lasers, until recently, were not so available. And even then, the scattering rate here depends on the nth power of the electric field. So this means intensity squared for 2 photons. When intensity is small, that works against you. But by the same token, it means if it goes up a little bit, you can win a lot. Incidentally, people in biology know about 2-photon absorption and do for a long time. There is a nice illustration of one of the effects, which is, I think, only recently appreciated as being interesting for fundamental physics. Here on the left, we have absorption by a single photon process in a liquid solution, and you can see that the beam is scattering a lot, and eventually it disappears because it's used up by the Beer's law attenuation. This is a 2-photon signal, and the scattering rate is only high where the beam is focusing. So in a setup like this, you can have a spatial resolution. And spatial resolution is a very interesting thing in precision measurements because spatial geometry determines the character of systematic effects like geometric phases. And the way in which this works for 2-photon excitation is surprisingly nice. So a laser gives you not constant intensity, but constant power. And the volume in which this power is scattered is determined by the beam waste, this W naught. So pi W naught squared is just the area. And the Rayleigh range, so pi W naught squared over lambda, is about the length over which the focusing takes place. And you'll notice these 4 powers of intensity, or 4 powers of beam waste, sorry, are canceled exactly by the 4 powers of beam waste dividing the power by the area to get the intensity, which means the scattering rate, the signal, has nothing to do with the size of the spot that you focus. It depends only on the laser power, on the wavelength, and on the density of atoms in the cell. And that means that you don't pay a price by focusing tighter or relaxing. You can choose your length scale, and your signal to noise will stay the same. Essentially, the number of atoms in this volume is perfectly compensated by the nonlinear scattering rate each time. In xenon, we were able in Michigan to see a signal, not to do anything with it at that point in time, but rather to excite for the first time by a continuous wave laser this 2-photon resonance in xenon. So this is 256 nanometers, 2 of these photons being absorbed at once. And then from the excited state here, they decay by fluorescence, and the PMT is counting photons at 905 nanometers. The high background, which is actually quite stable, is residual photons of 256 leaking through the bandpass filter at 905, even after being suppressed by 6 orders of magnitude. So it was a small signal, but it was there. And we were able to do for the first time this type of spectroscopy. The question is now what's required to turn it into a tool for fundamental physics, where instead of a squid or an alkali magnetometer, you may imagine shining a laser beam into a vapor cell with xenon and measuring spin precession like this. So it's not obvious in principle that this would work. Sorry, I thought I had, okay. I'm missing the figure which shows noble gas nuclear spin. But if you imagine this ground state being split into plus and minus, then this is the spin precession that you look at. This is the nuclear spin. And you would think initially that the electric dipole moment matrix, which couples to the excited state, has nothing to do with nuclear spin. To first order, this is true, but you have a hyperfine interaction. And the hyperfine interaction in the excited state is mixing together the nuclear spin eigenstates with the electron spin eigenstates. And this means that when the interaction time is correct compared to the hyperfine period, there is an exchange, and the spin precession of the ground state will modulate the fluorescence of the 905 nanometers from the excited state. And in fact, what's being modulated is the scattering rate of the 2-photon absorption. So when your noble gas nuclear spin precesses around, every time it aligns correctly with the circularly polarized excitation beam, you get a peak in the scattering, and then it goes around to the other eigenstate, and the scattering goes away. And so counting fluorescence photons as a function of time, you see a modulation at the Larmor frequency. I won't talk about this in detail, but in addition to the simple modulation of a scattering rate, there is a 2-photon refractive index. And so one can do Faraday rotation in the same way as is often done for alkali magnetometers. The plane of polarization for linear light is rotated, and this rotation can be built up by passing multiple times through a cell because it adds rather than canceling itself back. Given that, we looked a little bit at the history of pulsed laser physics because Isaac Abela and everyone else for several decades only did 2-photon absorption with pulsed lasers. The reason for this is exactly the nonlinear scattering rate. When it goes as intensity square, you want the energy of the pulse compressed into a short time. The instantaneous intensity is high, and you get a very big signal, even if it's only for a short time. This makes sense in a way, but it also makes your life challenging because you need some frequency resolution in order to do precision spectroscopy. Fortunately, also in recent years, we have the tool to start tackling this, and the tool is frequency combs. So when the pulses of a pulsed laser are phase coherent with each other, this means that you have, just like in Ramsey interferometry for the neutron EDM, coherent phase interactions between each subsequent pulse. And so if you count the number of pulses and build up, with only one pulse, you have a Fourier spectrum with a certain bandwidth. With 3 pulses, now you start to see the individual modes of the pulsed laser. And with more and more pulses, the modes become more and more narrow. And I've done this figure in a way such that the integrated area under all modes is constant. And you'll notice again that if the instantaneous intensity, let the atomic resonance be in the center here, if I have the blue curve, then intensity squared is not such a large number. If I have the red curve, now it's starting to get interesting. More interesting even than that is that if the resonance is here in the center, and it's quite narrow, because I'm absorbing 2 photons, there is a chance to take 1 photon from each of the modes symmetrically on the 2 sides. And these add up in a way that the detunings are canceling perfectly. So even when neither photon here or here is resonant to the transition, together they still make an excitation. And this means that the power, even outside of the bandwidth of the atomic resonance, is still contributing to the excitation, and the same here and here. I can use my full laser spectrum. And I can use it in a way that if I shift the center line just a little bit off the atomic resonance frequency, the scattering rate will drop because the resonance condition is also destroyed for everything else. And so like this, you can do a very precise spectroscopy and still use all of the laser power, even though the bandwidth is quite large. Going to more than 2 photons, the combinatorics is even more favorable, because if my atomic resonance is here, I can say take 2 photons from here and 1 from a farther detuned mode, but that's maybe farther in the future from being a realistic application. And then this is data from a proof of principle experiment using a ytterbium atomic beam and a picosecond pulsed laser. So this is just to show what happened the first time that we could get a signal or so. This is the count rate of a fluorescence photon. It has a similar level structure to xenon. And the signal goes away when the laser is off. It comes back when the laser is turned back on. And then when the atomic beam itself is turned off, this is a resistively heated metallic element in vacuum. It has some time constant to cool down, and that can be seen and measured. So it's, again, low counting rates, but this is a finite signal which can be optimized. And the way to optimize it, particularly for xenon, would look something like this. So this is the scheme to have in mind. The black lines are the modes of a titanium sapphire oscillator, and the red line is the position of an atomic resonance. It has to be actively stabilized, which is the real challenge. Luckily for xenon, this can be done with vapor cell spectroscopy of potassium. And with potassium, we can feed back on a beat note to the Ti-sapphire, and then what goes from the Ti-sapphire into the frequency doubling element that generates ultraviolet light can be absolute stabilized even in a picosecond spectrum. Picosecond is a word that you don't hear as much as you used to in pulsed laser physics. Most frequency combs are based on femtosecond technology, and there are good reasons for that, because the 1,000 times shorter pulses and the broad bandwidth mean that the signals can be larger for most applications that people care about. The problem is a practical one, because here, this difference in phase every pulse in time domain is a shift in the envelope of the frequency domain spectrum. And every time you go through a transmissive optical element, you have the chance to pick up an additional phase by chromatic dispersion. So now a mode on the left and a mode on the right may no longer have the same phase when they interact with the atom. And this is a chance to lose coherence so that all of the modes no longer add up and give you a nice coherent signal. With a picosecond spectrum, a bandwidth of 200 gigahertz or so is reasonable. This can be brought into the ultraviolet without too much distortion. The distortion can be compensated. With femtosecond, we now talk about 25 terahertz, and the chromatic dispersion is terrible. I'm not aware of any present-day technology for compensating the acquired phases at a level that would be sufficient to do precision spectroscopy in the way that we need for an EDM experiment. But fortunately, all of the picosecond technology exists, and there are still companies selling it. It's just that no one had a physics case for it in the last years. And the reason this is maybe not an obvious thing to do is because the absolute stabilization is difficult when you can't frequency double a comb and reference it back to itself. The bandwidth is so narrow that one of these modes in the frequency doubled spectrum is completely far away from anything in the original laser, and so you can't interact them at all. But you can use this atomic resonance of something like potassium when you're lucky enough to have it, and xenon is lucky. There are other approaches to doing this, but ultimately the point is to build a frequency comb which sits by itself perfectly stable in this little frequency window, which is interesting to do the spectroscopy on xenon, as I described before, and to see what kind of resolution as a magnetometer and in principle as an EDM experiment component it can then deliver. And again, the technologies for this are there. Not only have the lasers improved in recent years, but the photomultipliers for detecting this near infrared fluorescence have gained orders of magnitude in their sensitivity. And I don't think that silicon technology is there yet, but there are other semiconductors which may provide new options in coming years. Anyway, we have somewhere to start, and the data that I showed you before with this reasonable signal to noise, but kind of sad signal to background, this is not the signal to noise that you would expect if you did the same experiment again today. So this is the sort of 0th order approach to be built up from now. And then this is something that I think a few people in the audience will recognize because it's a calculation we had to do for the xenon EDM. I wanted to just close by mentioning that this comes also in neutron physics, and that the origin for knowing this equation, the structure factor of scattering for a correlation function with cold or thermal neutrons, is connected by a theorem into the velocity correlation function, which is used to calculate the moments of a polarized xenon distribution in a cell. Not only does it tell you for the xenon EDM that the geometric phase was small, but it shows you exactly why it's a good idea to build a detector for xenon with spatial resolution. Because now we talk about the geometric phase not as a moment distributed across a cell with a centimeter, but the geometric phase associated with a laser beam focused to 200 microns. And so we've already done the bookkeeping and the calculation to know why this is a good idea. I think the challenge is a practical one, to build it and see if it compares in reality with what we can write on paper. So with that, the interesting content is done. I would like to thank all of my colleagues at Heidelberg, at the ILL, the group at Michigan where I did my PhD, and in particular, Jaideep Singh, who joined the Michigan State University and provided the laser for the first xenon data that I've showed. And we're going to try and continue doing it at Heidelberg. So if there are motivated students and postdocs out there who think that these sound like cool ideas, please contact me. And in closing, I would be happy to take any questions from you.